Optimization of yield lines in two-way slabs. This video will deal with type 1 slabs. First, we start with the definition of the different slab types. Type 1 is a rectangular slab with all four ends simply supported. Type 2, there is one end of the slab which is fixed. Type 3, you have two opposite sides of the slab who are fixed, the other two simply supported. Type 4, you have two adjacent slabs, two adjacent fixed ends of the slab. Type 5, you have three fixed ends of the slab, and type 6, all ends are fixed. This video will now deal with type 1 slabs. Take a type 1 slab with width A and length B. Using the method of yield lines, we know that the axis of rotations are at the support edges. So you have four axes of rotation. Where two axes of rotation cut each other, there starts a yield line. So we draw this yield line. The angle beta 1, we do not know. We will calculate the angle beta 1. So I will treat the four corners with a different angle, beta 1, beta 2, 3, and 4. Where those two yield lines cross each other, then there's a next yield line connecting those 2 points. Now we will talk about some geometry that will appear in all the slides of this playlist. And S1 is this distance as indicated here, S2, S3, and S4. This is only valid for two-way slabs. It means that B, this distance, is between A and 2 times A. Because of the geometry, S1 plus S3, of course, must be smaller than B. Otherwise, you have not realistic yield lines. And S4 and S2 are equal to A. We will use the cotangent's rule of a triangle, which means that the height of the triangle is equal to the largest side of the triangle divided by the sum of the cotangents of the two angles here. Now, we know that the cotangents of 90 degrees minus beta equals the tangents of beta. So for S1, it becomes the largest side A divided by the sum of the cotangents of this angle is the same as the tangents of beta 1. And this is the tangents of beta 4. So now for each one, like S2 and S3, we can write down the dependence of the angle. For S2, for instance, when you see S2 here, then you see very clearly it is S1 multiplied by the tangents of beta 4. When this S2 is equal here in this side, you can see it. Then we do the same for S3 and S4. So now we have a relationship between the geometric characteristics and the angles of the yield lines. Not every yield pattern is valid, because every yield pattern must consist of a rotating or a movable mechanism around the rotation axis. So this means that to have a realistic yield line pattern, the distance Sx, which is mentioned here, and which is S1 times tangents beta 1, must be equal to Sy, which is S3 times the tangents of beta 2. So those two must be equal, Sx must be equal to Sy. Then it gives you this relationship. We can do the same with Sv and Sw, and it gives us another relationship between the different angles. When we combine them, then you see that S1 divided by S3 is tangos beta 2 divided by tangos beta 1, and it's also equal to tangos beta 3 divided by tangos beta 4. This means that you can, of the 4 angles, to obtain a realistic yield line pattern, you can get rid of one parameter. It means one of the corners, because one of the corners is expressed as a function of the others. You can use beta 3, but you can also say beta 2 is equal to, or beta 1 is equal to. That doesn't matter. It's just that one of the angles is dependent on the previous 3 angles. Now, because of symmetry rules, all angles here in our case must be equal, because there is no difference between this case, which is a long side simply supported, and a short side simply supported. This angle has also the same long side and the same short line as simply supported, and it goes for this angle and this angle too. So it's not possible that you will obtain different angles. So that saves us a lot of work. So we know now that all angles are equal to beta, and because it's difficult to work with angles, we will work with a parameter I call x equals tangos beta. So the tangents of the different angles here is a parameter. Then we can rewrite S1, which is A divided by tangos beta 1 plus tangos beta 4. So S1 is A over 2x. We can do it the same for S2, and S2 is then A over 2. And for S3 also, we can rewrite it, and then you see S1 is equal to S3, and S2 is equal to S4. This is an important relationship because it means that in a symmetric element like this, the size S1 is always equal to S3, and of course S4 is equal to S2. We know that we got the different geometrical parameters, and we check just to show that this rule, you always have to check to see that you have realistic yield lines. But of course, in this case, it's evident because tangos beta 2 is equal to tangos beta 4. So, and beta 1 is equal to beta 3. So this equation is valid, obvious valid. We will now calculate the work done by the loads, and we divide that by Q times delta, and delta is a unit displacement. Then we know that, for instance, this portion here consists of triangles. The surface of the, or the total load is S1 multiplied by A times Q. And the mean deflection of a system that consists of triangles is delta over 3. So this is this element of the equation. On the opposite side, we do the same. Triangles, it's A times S3 divided by delta over 3. So now we got this element. What is left is a summation of rectangulars. So the mean deflection is delta over 2. And the total surface is, of course, B minus S1 minus S3, which is the length of this piece, times A. So we can now, with those simplifications for this type of slab, we fill in the different variables and we obtain this nice equation. The work done by the internal forces or bending moments and is then d divided by m over delta, because it makes it easy to calculate that. The maximum bending moment is m alongside the yield lines. To calculate it, we have first the yield line, like here, this yield line. It will be projected directly to the axis, the horizontal axis here. the length of this axis is b, and the angle of rotation is delta divided by S4. So that's the delta, b over S4. On the left-hand side, we have the total length projected on the rotation axis is a, divided by the angle of rotation, delta over S3. So it's a over S3. So we do the same with this yield line projected to this axis of rotation and for this side. So that's why there are four elements in the equation. We fill in the different parameters and we obtain this equation. Now we know that the work done by external forces must be equal to the work done by the internal forces. So E is equal to D, or we can get M out of this equation, and M is then a function of alpha. Alpha is B over A. That makes it easier to handle. Alpha is B over A, and X is the tangents of beta, the tangents of this core. So now we have a formula which gives us the bending moment. It's not yet the maximum bending moment. It's just the bending moment related to a certain yield line pattern. Now let's maximize this function, or make look for extremes. So the first derivative of this equation to x, because x is our parameter, should be put 0. And then we can, from this equation, we can calculate x max. It means we can calculate the angle which gives us the maximum bending moment. And x max is then equal to this pretty formula. Something we should notice, x max, when you take the limit to infinity for alpha going to infinity, it means that you are going from a two-way slab to a one-way slab. Then you will see that this is the 1 over the square root of 3, the limit for alpha very big. It means that you would divide that by that, or it's 1 over square root of 3, which is the tangents of 30 degrees. Beta max is expressed in degrees, is then of course 180 divided by p, and the arc tangents of x max. This is beta max in a graph. X-axis, it's alpha from 1 to 2, and the beta varies from 37 to 45 degrees. This beta max, when we are looking at alpha bigger than 2, but this is not valid, but it gives you an impression of is this formula right, then we'll end up with 30 degrees. It will always be bigger than 30 degrees. The 30, 45, 60 rule that we use for making yield lines without optimization, well, in our case, because it's 2 times it, because all sides are simply supported, so the angle beta is 45 degrees. So it's here on that side. So it means that if you optimize the yield lines, you will end up with an angle which is smaller than 45 degrees. And this angle depends on the ratio of length divided by width of the slab. Let's now look at an example. We have a rectangular slab, size is 6 and B is 9 meters, and it's loaded by 10 kilonewton per square meter. The bending moment, maximum bending moment obtained by the rule 30, 45, 60 can be found by using our previous formula with alpha stay the same, and of course x is 1 because we use 45 degrees in our 30, 45, 60 rule. If you fill it, you can fill this in, you obtain this equation. It's a function of alpha. So this is the bending moment, the maximum bending moment if you do not optimize the yield lines, and it gives you 21 kilonewton meter per meter. Now we are going to use beta max instead of 45 degrees for alpha equals 1.5, because 9 divided by 6 is 1.5. We see that beta max is 40 degrees, not 45. So the dotted line here gives you the 40-degree line. So you see that the yield lines are a little bit adapted to find the optimum. And when we can now calculate this, and we find 21.2. Immediately we see that the difference is not very big. Of course, because the yield lines here between the dotted ones and the full line, the difference in length is minimal. It's not that large. So we expect that this is not going to differ a lot. We can now also make one formula for M max. We just take the previous formula and we substitute x by x max to find the maximum or to have the maximum. And after some arithmetics, you will find this formula. So now this formula gives you directly the maximum bending moment, the optimized maximum bending moment for each slab of type 1 with alpha between 1 and 2. We can now divide the bending moment obtained by the 30, 45, 60 rule, and we divide it by the optimized bending moment, then you will see that the difference is always less than 2%. And the difference gets bigger when alpha gets bigger. So in reality, most of the time we are working around this area. So 1%, it's a small difference. So we can conclude that the difference with 30, 45, 60 rule is less than 2% for type 1 slab. Unfortunately, it's bigger. When it was smaller, it doesn't matter. But now it's bigger. So you should always be careful with that. 2%, that's fine. There's no problem by that for type 1 slabs. We can use a simple way. We can say, for instance, that the bending moment is QA squared divided by a coefficient. And this coefficient, we can use in of the previous slides, the bending moment M dependent on alpha and X, and we can calculate K now, the factor K, and it's given by this formula. This formula, for instance, for alpha 1, which means it's a square slab with x1, that means 45 degrees, we get 24. So the maximum bending moment is qa squared over 24, and this is exactly the value that we expect to find. Now we can also fill in x for x max equal to x max, and we find the k value, which gives you the maximum bending moment, and this is expressed in this equation. Why do we do that? Well, this side of the equation is totally independent, or is only dependent on the geometric characteristics. So this is nice to know, because it's independent of the load. It's only dependent on the characteristics of the slabs, and it's only depending on the ratio length divided by width. So now when we look at a slab with alpha 1.5 and A is 5 meters, so this is 5 and this is 7.5, with a load of 20 kilonewton per square meter, we calculate the coefficient K max for 1.5. You see that's the only parameter I need. And we have 17. So the bending moment is 20 times 5 squared, Q8 squared, divided by 17 is 29.4. So you see that it's getting very easy and quick to get the maximum optimized bending moment.